I'm just wondering, are we using this laptop or web?
Yes. Yeah, because the thing doesn't have any audio, so you can't speak through this computer. Yeah. Okay. Why is this software modeling and design? Don't I did it again. Okay.
You send us the Zoom
The Zoom link is I will send you the Zoom link.
Okay, yeah, I was gonna ask about this. There's like a ton of things. Like we can't finish this one out. But I mean, since we don't finish it. I think I think so. Fine, question. I think there's two from each part. Like we have two. That's two. In my opinion, I only saw okay. And you all on the playground. And then no. I think skip the Turing machine one way quick. Because that seems like it would take a long time. No worries. Yeah, you can do something. And then we'll see and how do you want to see if we have time to do the second one. But do you want, how do you want to format? Do you want to you just give them answer, you skip questions like what and then at the end we say the solution, or do you want to like give them one by one, so you give them time what you want and make the solutions. Maybe perfect so you want solution and go with the so I do the transport and I go with because like just like over there. Well, I think I'll say well, let me shoot that 25 minutes for my I mean, we'll see how it goes. Okay, sure. Oh, sure. Okay.
Okay, we're having a problem with the live stream. It's being forwarded to software modeling and design. That is about right.
No worries. Wait, is it oh.
This workshop, all workshops.
I can say
Now it should be okay. Hopefully.
I'm not sure. This is my first time to use this feature. This Zoom feature.
Yay! Okay, it's working. That's good. Right, we're live on YouTube. I call it this one. I will send you guys the Zoom link so you can join. Not the people on Zoom. I'm talking to the center. This is Thomas, by the way, everybody.
Hey, hi everyone. I'm Thomas.
I will not. Now I can hear myself speak twice. Okay, this is better. Okay, on slide, is that good?
So I'll join the Zoom by myself. Yes. Whoa. I think while you go through your part, I'll try and make like the worksheet questions nice later. Yeah, sure. Yeah. I'm just trying to share the Google Docs today. Nah, it's ugly.
Okay. So whenever you want to present, can you please share the screen on your laptop when you're trying to join the Zoom. Well, the main thing is going to be through this one. Okay.
So it's very interesting. Yeah, just like yeah. Are you going to introduce the season slides?
Yeah, I'll do those ones. Oh my God, there's a lot of people online. I just realized, oh, finally, okay, it's working. All right, and on Zoom, I will share the slides that we have. So the same slides that you sent on the slide.
Yes.
Yes. All right, cool. Are you ready?
Yeah, I'm ready.
Okay. Stay muted. All right. Oh, there's a message on Zoom. Will the questions and solutions discussed today be posted anywhere? Yes, we will try to post them. Okay. All right.
Yeah, so it's just like
Okay, cool. All right. I'll pull up a microphone. I would recommend you use a microphone so that people can hear you as well. Okay, cool. Hi, everyone. Hello. Thanks, everybody, for making it today. Welcome to this vision workshop is running for the very first time, at least in the 2 years that I've been on the team. But yeah, so I am confident that this will go really well, and I hope you all benefit from it. Before we start, I'd like to take a moment to acknowledge the traditional owners of the land on which we meet today, the Wurundjeri people of the Kulin Nation, and I'd like to pay my respects to their elders, past, present, and emerging. Next up, I want to present our tutors. Jiwon unfortunately couldn't make it today. She's really sick, but I'd like to do a quick shout out to her because she helped out with the content. She helped out organizing this whole thing. This is Thomas, everybody. Hi, Thomas, say hi. Say hi.
hi.
And Lito, hello. Can I say hi?
Hi.
Okay, cool. All right, you've got your presenters. But before we get actually started, I want to do a quick disclaimer. This workshop is not officially endorsed by the university or the teaching staff and may not fully reflect the accessible subject content. Any tutors that participate in this workshop have verbally chosen to do so voluntarily and are not expected to represent the teaching team. Okay, so we run revision workshops every semester, blah, blah, blah. You remember? You can scan this if you're not a member. We have events. No? Okay. All right. And we can get started. Go ahead. And I'll sit on the side. Do you want to keep an eye on Zoom or should I?
I will share the screen.
Yeah, so this is shared. Yeah, you can share. You want to share your screen there? Okay, I'll stop sharing. You go ahead. Perfect. All right. And it's like this one. Do you want to turn your camera on?
Yeah.
Yes. And you have to connect it. So people actually never mind. Never mind. No, never mind. Yeah, it's all right. Yeah, because I just realized because we also need to show it to them. Okay. Did you stop sharing? Okay. It's okay. Yep.
just going to talk about Computation and I'll leave the presentation.
Cool.
Okay, hi everyone. I'm Thomas, and I'm going to talk about the regular languages, including DFA, NFA, and PDA as well, and colon reference as well. So this is about the second half of the subject, the before Turing machine and after the logics. So this is the main focus of this workshop because we realize students usually confused about the second part of the subject instead of the first part because after you cover the DFA and NFA, you realize this is the hardest part of the subject. So that's why we're going to have 1 hour revision for the second half of the subject. And then the second hour we'll be focusing on doing some past paper exercise and we'll go through some answers as well. So this is our plan for today. So okay, first of all, regular languages. All right. So for regular languages, we have three tools to represent it. First of all is DFA and NFA, and then we also have regular expressions. So DFA, we have one initial state, same as the NFA, and as state as well, we have more than one or zero as state. If the DFA or NFA have zero as state, that means the language of that DFA or NFA is empty, and we say that the DFA and NFA is empty. Thank you. And for the definition of DFA and NFA, the main difference is in the transition function because in NFA we have non-determinism. So that means given a state and a symbol, an input symbol, in NFA we output a set of states instead of in DFA we only output a single state. So this is non-determinism. That means given if we are in the same starting state and input symbol, we can take multiple paths. If one of the paths can accept the input string, then that string is accepted. So this is non-determinism. And for it also has an absolute transition. That means we can transit to another state without consuming any input symbol. So this is a characteristic of NFA compared to DFA. And another one, yeah, just like what I said before, we can have multiple choice of transitions. So in this example here, we starting from the stage one, and then we consume the input symbol A. If we consume the input symbol A, we can take either going to stage 2, stage 3, and stage 4. And if one of the path can accept the input string, then the string is accepted. So we don't have to make sure all the path can accept the string. We just need one of the path accept the string. Then the string will be accepted. So for this one, the transition function from 1 and the input symbol A will output a set of states 2, 3, 4. So that's the realization in the definition of NFA, talking about non-determinism. Another focus of regular language is also the cultural properties of regular languages. So when we talk about cultural properties, that means given a language, given two languages A and B, let's say both of them are regular languages, and if we take operation, a Boolean operation, let's say union, and we say regular languages is closed under union, that means the union of A and B is regular language as well. So after taking that Boolean operation, the resulting language is also under that class of languages. So let's say we have a DFA, MA for the language A, and FA for language B, MD, and we can construct NFA by connecting them using an epsilon transition from the initial state. So, and then the constructing NFA is recognizing the union of language A and language B. And just talk about the definition of regular languages. If we can construct DFA or NFA, or we can come up with regular expressions, then that means that language is regular language. So that's why I didn't say DFA MA for regular language A, because we can already know if we can construct DFA for language, then that means that language is regular language.
this is quite important when you do the reducibility, because in the reducibility, sometimes we will use this definition and also this cultural property as well. Because let's say you are constructing let's say you are constructing new Turing machine for two languages, then we can construct for two languages, and we want to recognize the union of two languages. Then we can construct using some systematic algorithm. Let's say this one, we can construct an NFA to recognize the union of A and B. So it's just connecting the two to DFA using an epsilon transition in the from the initial state, and then the NFA will be recognizing the A union B. Intersection as well. So this is taken from the tutorial questions. Let's say we have DFA to recognize any string that has even number of A's, and another DFA to recognize any strings that has one or two B's. Then the set of states in the new DFA for the A intersection with B is the Cartesian product of the two sets of states in DFA and DFA. So let's say the set of states in DFA is 1, 2, right, from here, and then the set of states in DFA is 1, 2, 3, 4. Then the Cartesian product of two sets of states is 1, 1, 1, 2, 1, 3, 1, 4, and something like that. And the first coordinate in the new state is representing the state in the first DFA one. So if we're in the initial states of the new combined DFA, then 1, 1 means the DFA the DFA1 is in the stage 1, and the DFA2 is in the stage 1 as well. So because the first coordinate is representing the state in DFA1, and the second coordinate is representing the DFA is representing the state in DFA2. So we are like 1 and 2 DFA concurrency, and then we have to monitor the transition of states in both DFA using a 2D, let's say a 2D, two-dimensional state in the combined DFA. And if how do we determine the accept state in the combined DFA? So because intersection means we have to accept a string if the string is in both of the languages, is in both language A and language B. So if in the combined DFA, we have to, if it's an accept state, then that means the first coordinate is one of the accept state in DFA1, and the second coordinate is one of the states in DFA2 as well. So that's why, because the accept state in DFA1 is 1, and the accept state in DFA2 is 2, 3, that means the accept state in the combined DFA is 1, 2, and 1, 3. So we are like 1 and 2 DFA concurrency. For complement, okay, so this is easier, I think, because intuitively, if we take a complement of the language, that means when we have a string that is accepted, then we reject now. If we have a string that is rejected, then that means we can accept now. So that means in the DFA, for the complement language, we can swap the accept state to and non-accept state. So that means if it's accept state originally, we change it to non-accept state. And if it's a non-accept state, including initial state, then we change it to accept state. All right, concatenations. So if we have a DFA for language A and we have a DFA for language B, they call it D1 and D2 here. And then concatenations means we take a string from language A and then we concatenate it with another string in language B. So we take the DFA D1 first, and then we connect the accept state of D1 to initial states of D2 by epsilon transition. And then we remove the accept state in D1 because we just want to accept it if it reached the accept state of D2. So this is concatenations, and we can see that we can construct a NFA for the concatenations of two languages. That means regular language is closed under concatenation. All right, so Canista. Actually, we can prove this because Canista is any number of concatenations, including zero of strings from language A to form a concatenated string. That means by the closure properties of concatenations and the definitions of Kleene star, actually we can prove that Kleene star is closed under regular language is closed under Kleene star because Kleene star is any number of concatenation of strings from language A, and because concatenation regular language is closed under concatenation, so that we can prove regular language is closed under Kleene star as well. But actually, we can also construct an NFA for Kleene star. Let's say we have a DFA for language A, then because for Kleene star, we always have empty string in it. So first of all, we accept the empty string first. So if we want to accept empty string, that means the initial state has to be accept state as well. So we have to make the initial state to be a accept state here, and then we take the absolute transition to the initial state of the original DFA. And because Kleene star is any number of concatenations of strings from language A to form a concatenated string, so that means we have to connect the accept state in the original DFA to the initial state of the original DFA, such that we can keep concatenating any number of strings. So this is this operation. We connect the original accept state in DFA1 to the original initial state of the DFA, such that we can keep concatenating any number of strings. So this is Kleene star, and because we can construct NFA for the Kleene star of the language, that means regular language is closed under Kleene star. Okay, difference. We also are using the previous closure properties of regular language because to prove that regular language is closed under difference, because A minus B equals to A intersection with B, intersection with the complement of B, since regular language is closed under intersection and complement as what we have proved before. So A difference B is regular. All right, reversal. I think this one we didn't cover in the lecture, so it's all good. So when we talk about reversal, that means we have a string, let's say 0100, and the reverse of that string is 0010. And let's say we have an original DFA like this, then we just have to make the accept state to be an initial state using an epsilon transition from the initial state of the new NFA. And then we make the original initial state to be a accept state. And because in the DFA, we only have one initial state, that means we only have only one accept state in the reversal NFA. All right, pumping lemma. For pumping lemma, we have two versions. One is the regular language, and another one is for context-free language. And remember this because students often confuse about this too. We have two versions of pumping lemma, and regular language and the pumping lemma for regular language is simple. So the pumping lemma for regular language is stating that for any regular language A, if A is regular, then there exists some pumping length P larger than or equal to 1. So the P is positive. For all strings in the language A, if that string, the length of that string is greater than or equal to P, then there exists a XYZ in the there exists a XYZ, there is a string. Then S can be written in XYZ such that Y is not empty, the length of XY is more than or equal to P, and for all I larger than or equal to 0, x, y, I, z is in the language A. So this is the part that we say, how do we pump it up or pump it down? If I equals to 0, we say that we refer it to pumping down the string because we remove the y. And when you say pumping up, that means we want to pump up the y. So I is larger than or equal to 1. So that's why the name is pumping lemma, because we are pumping up the y or pumping down the y. So this is pumping lemma, and how do we use this one to prove language is regular? So because A is regular, if A is regular, then this statement, the conclusion, will be true. But if A is not regular, and we assume A is regular, but actually A is not regular, then the conclusion should not be true. That means the first part here, 1, that should be true here. The condition should be true for the implication. The condition should be true. And the conclusion of the implication is false. Then we reach on contradiction. So, so that means the conclusion is false. And in other words, is the negated version of the conclusion is true. So we try to negate the conclusion. So when we put a negation here, that means for all p, because that is there exists here, then the negated of the negated version of that exists is 4. For all p larger than or equal to 1, and there exists some s in the language A, and the string s is larger than or equal to p, and because we put a negation here and we negated the whole conclusion, and then we want to prove that this negated conclusion is true, then A is not regular because we reach a contradiction here. So this shows that how do we use pumping lemma to prove a regular language is not a language is not regular. So we first assume the language A is regular first, and then we take any pumping length P, do not specify a P, and we design a string S in the assumed regular language A with a length at least P. So we are using the P to construct a S. So let's say, for example, S equals to 0P, 1P, and then we can make sure the length of S is larger than or equal to P. Then we show that any way of breaking down S into X, Y, Z cannot make all statements true. So the false statement is S, X, Y, Z, and Y is not empty, and the length of X, Y is more than or equal to P. And if we want to pumping up or pumping down Y, then that should be in A as well. But we want to often we assume S equals to X, Y, Z, the length of X, Y is more than or equal to P, Y is not empty, and we pick a J larger than or equal to 0. So we try to pump or pump down the Y to see if the resulting string is in A or not. Then if we try all the possible case of the splitting the S into X, Y, Z, and we see that the resulting string is not in the language A, then that means we reach our contradiction, and then we can say that A is not regular. That means because we assume A is regular, and if we reach our contradiction, that means our assumption is wrong. Then we say A is not regular. There's another version for context-free language as well. So the main difference is we split the S into U, V, X, Y, Z, so it's more complicated compared to the regular language of pumping lemma. So S equal to U, V, X, Y, Z, and the length of V, X, Y smaller than or equal to P, and the Vy is not empty. That means the length of Vy is larger than 0, and we want to, this time we not just pumping up or pumping down Y. This time we are pumping up or pumping down V and Y at the same time. And equivalency because if the language is context free, then the conclusion of this implication should be true. But if A is not actually context free, then that means the condition is true, but the conclusion is false. Then, in other words, that means we can negate the conclusion. So we negate the conclusion here, and then we want to prove that the negated version of the conclusion is true. And then we say that A is not context free. So over here, you can see that we are considering all the possible splitting of S into U, X, Y, Z, but not just consider one specific split of U, X, Y, Z. So that's why we have to consider all the possible cases of splitting S into U, X, Y, Z, such that we can prove, such that we can reach a contradiction, and then we can say that A is not context free. Because students usually confuse why actually in the pumping lemma for context-free language or in the regular language version, pumping lemma is saying that there exists a UA XYZ or there exists a XYZ, such that but why do we in the contradiction we want to consider all possible cases of splitting S into UA XYZ? Because we have already negated the conclusion of the pumping lemma, and then we want to prove that all the possible splits in the UX cannot make the four conditions true. So we are because we want to break the there exists statement. how to break the data access. We prove that for all cases, the statement does not hold. So we have to consider all the possible cases of splitting the S into U, X, Y, Z. This is pretty similar to the routine of proving language A is not context-free using public lemma. So we have to assume the language is context-free first, and then we take any P, don't specify the P, and then we design an S in the language A, at least as long as P. And then we show any way of breaking down S into U, X, Y, Z cannot make all the four statements true. And then if we show that any possible cases of splitting UX, X, Y, Z cannot make this statement, this fourth statement true, then we reach a contradiction. And then we can see that A is not context-free actually. All right. All right, okay, so we finished the regular language part, and then we jump into the context-free language, and we talk about pushdown automata. We have two realization of context-free language. For the first one is PDA, the second one is the context-free grammar, and then we talk about PDA first. And then compared to DFA and NFA, we also introduce one more component in the definition, that is the stack alphabet, because we can have a stack in the DFA to help us to memorize some input. And then we also have a transition function, and there's some changes as well. So compared to DFA and FA in the PDA, we given state, input symbol, and the top stack symbol. We output a set of turbos of the next state and the new top stack symbol. So the main difference is we have a stack, and that help us to memorize the input string or memorize what operation we have done. Right. So yeah, because the addition of the stack allows the PDA to recognize languages like A, N, and B, and then we can ensure the length of A, and then the number of A and the number of B are the same. The stack does not need to be empty when the machine stops. Yes, and including exception. Yes, because when we accept the string, then the stack doesn't have to be empty. We just have to ensure the machine is in the accept state when we accept it. And then we compare to Turing machine, we also have to make sure the input string is consumed. The input string is exhausted, so such that we can finish the PDA. And then if after we consume all the symbols in the input string and the PDA is in the accept state, then we can accept it. Compared to Turing machine, we don't have to consume all the symbols in the input string. As long as it reaches the accept state of the Turing machine, then the Turing machine can stop. All right. So this is a main difference between PDA, NFA, and DFA, and the Turing machine. And also, anti-stack cannot be popped. If we pop the anti-stack, then we reach then we have to reject. Transition functions and notation, yes. So the first coordinate in the first part in the left-hand side of the arrow is the input symbol, and the second coordinate to the left of the arrow is the top stack symbol. So if it is epsilon, then that means we doesn't have to consume the top stack symbol in the stack. And then we push dollar sign to the stack here. And if we reach Q1 and if the input symbol is A, and then we push the A into the stack. And then here we are consuming one A in the stack. And then we do nothing. And just so over here, we just consume one A. And then we also are consuming A because we want to make sure the number of A is equal to the number of B in the string. If the number of A is equal to the number of B in the string, then we can accept it. Sometimes we use dollar sign to mark the bottom of the stack. So the usage of the dollar sign here is marking the bottom of the stack. And when do we use the dollar sign to mark the bottom of the stack? Usually if there's like something like symmetric properties of the acceptance string, then we can mark it so that we can ensure when we accept the state, the stack is empty. And if we want to ensure the stack is empty when we accept the state, then we can use the dollar sign to mark the bottom of the stack. Yeah. And then a language is context free if only if it's recognized by PDA. Yes, because if we can come up with a context free grammar or pushdown automata, then the language is context free. The same as the regular language, if we can come up with a PDA or an FA or regular expressions for that language, then the language is regular. All right, so this is talking about the conversion between context free grammar to the PDA. So let's say we have constraint grammar over here, and then we set up the PDA something like that here because the terminal is XY, and then we push the dollar sign to mark the bottom of the stack, and then we push the S symbol into the stack because S is the initial Wu name. And then we have a terminal X and Y, then we push if we have input symbol X and Y and the top stack symbol is XY, then we try to pull it. And then if after we consuming all the whole input string, and if we reach the dollar sign in the stack, then we can accept it. And if we have a rule, let's say x a y, then we push y first. We replace the rule name a into y, and then we push the alphabet. We push the symbol in a reverse order because we can only because it's a stack. We can only read the stack from the top. So we are pushing the terminals in a reverse order. So we push Y first, we push A, and then we push X into the stack if we want to apply the rule A. So this is a systematic algorithm to convert context-free grammar to a PDA. And there's not a high chance to cover it in the exam, I think, because it's just a systematic algorithm. All right, so that's for context-free language. And thank you, everyone, and I'll pass it to Lezhou to talk about Turing Machine. Thank you, everyone. Thanks.
You think I can find the same thing in draw?
Why not? Yeah, it's only that. But I don't know if you could log into the people. What kind of is it a USB-A?
See?
USB-C or
Oh, wait, sorry.
This is not
wrong,
USB-C.
wrong way.
Yeah, that's what I was thinking.
Yes.
USB-A. I'll just put it there. You can put it.
Yeah, don't close this. Okay. Yeah, no.
No? So much. You can do it with that one.
It's okay. Oh, I just use.
You can use the white markers and
No, but that's not recorded though. Yeah, it's good.
if you like, you can just share your screen and share that one.
It's too much work.
Yeah.
Fine. Hello. All right. Thank you, Thomas. All right, on to Turing machines, the sort of next step in computation. Oof. All right, so just some stuff to highlight the difference with the previous automaton. All right, so as usual, there's one initial state, and then so PDAs can have multiple accept states, and Turing machines have one accept state. So okay, this is kind of an important distinction because the nature of the accept states in the two automaton are it's not really the same exactly because in Turing machine, once you go into the accept state, like then you're finished, then you halt, and then like you accept. But in PDAs, for you to accept, you have to be in the accept state, and you have to finish with the input. So that's why it is like that distinction. You don't. It's possible to then go out of the accept state after like another input, let's say. Okay. What else is there? States. Yeah, that's the same. Okay. And then maybe I'll. Okay, this is a bit hard. Whatever. There's also the input alphabet. So the input, I guess, it will start on the tape for the Turing machine, and on the PDA, it's like being fed in left to right as usual, like a DFA, for example. Oh, thanks.
Maybe it's
All right. Transition function, we'll talk about that later. Okay, so PDAs also have the stack, right? But Turing machines, they don't have a stack, they have the input. Which is important because with the tape, which is important because when you do like a transition, you can go left to right instead of just like being at the top of the stack. So that kind of makes it more powerful. All right, and then there's accept state, and then there's explicit reject state. So once you go into the reject state, then you just halt and reject. Great. Yeah, we'll talk about transition function later. All right, so this is a bit of a visual graphic here. So the head of the tape is at any time pointing at one of the cells of the tape, and then a transition can tell you to go right or go left. And before it does that, it can also tell you to like read from the tape and overwrite the current tape cell. All right, here's the transition. How do I get rid of this? Whatever. Yeah, sorry, I didn't prepare this part of the slides. Okay, so the transition function, what are the inputs? It takes the current state and it takes the current cell, what the symbol at the current tape head. And then, so for example, here let's say it's at Q0, the state, and then it reads input 0 from the current tape head. This transition function defines it goes to the next state Q1. It overwrites with a hash and then goes right. All right, and then yeah, that's just another example. Okay, so there's a bit of a difference between the other automaton and Turing machine, right? The other automaton we have, they can accept and reject strings, right? So they accept strings that are in the language they recognize, and they reject strings that's not in that language, right? Well, that's similar for Turing machines, but there's a bit of a finer detail in terms of rejection. There's kind of two ways that a Turing machine can reject a string. One of them is it goes into a reject state, right, and then it halts. But it can also go into an infinite loop, which is sort of a problem, right? So because if you're trying to show like if you're trying to decide whether some string is in the language, like if it loops forever, then kind of really hard to tell if is it in the language, like will it eventually halt or will it go forever and reject. So we make this distinction between the class of Turing decidable languages, or we can just call them decidable languages, where in terms of rejecting, well, they have to halt, they're guaranteed to halt. But if we don't have that restriction, and we can say they can reject by infinite looping, well, we can call that class of language languages Turing recognizable or recognizable. Okay. I guess one more sort of thing that you can might have noticed in the previous automata, when we're describing the languages they recognize, it's kind of more natural. We're calling them languages, right? For example, like the languages of all palindromic strings. So like, but now when we're talking about Turing decidable and Turing recognizable, now it's a bit more natural, like a bit more likely for us to talk about them in terms of like their problems, right? We're using that vocabulary. And I don't know if you guys remember from like the lectures and stuff, but it's not just stuff like, so let's see if the string's a palindrome. We can like input a string encoding of maybe like a Turing machine or a DFA or a PDA or something or a CFG, and let's see like a property of it, like will it accept this string or will it halt or something like that, right? Cool. All right, cool. I actually prepared this part of the slides, so I think I'm a bit more prepared for this part. So reducibility, I guess, okay, so this is a pretty, I think generally people say this is a pretty tricky part of the course, so feel free to let me know if I'm going too fast, or feel free to interrupt with questions or anything. All right, so what is this topic? What is reducibility? It revolves around this central idea that a problem can be used, like if you can use the solution of solving a problem to solve another problem, and we'll look at that we'll look at examples of that. And this relationship between languages or problems, we're going to manipulate that to reason about reason about decidability usually, but we can also reason about it for recognizability, although like you need a special kind of reduction for that. We'll talk about that later. All right, so what do I mean about reasoning about the decidability of a language? We can show that a language is decidable. Well, I mean, that's not new, right? Because like what would be the usual way of showing a language is decidable? I mean, we just use the definition, right? A language is decidable if and only if there's a decider for it. So just construct a decider for it. Well, okay. I guess with reduction, you might implicitly be using it actually. If you're using an existing decider and building on top of that, you're implicitly using reduction. Okay, so maybe we'll see that in the example. Actually, we will see that in the example. We can also go the other way. We can show that a language is undecidable. But that's not new, right? We've seen how that can be done. In the lectures, if you recall, they proved that Turing machine acceptance, ATM, to denote that language is undecidable. And then they use a technique called diagonalization to prove that. So yeah, hopefully you remember that. Oh yeah, also, maybe you'll be thankful to know that I don't think there's a pumping lemma for decidable languages. All right. Okay, I'll try erase this Q. Okay, great. All right, so I guess here's an example of what I was talking about, using a solution to a problem to solve another problem. And I guess this is a good example because it's pretty simple. So you're familiar with, we defined Turing machine, not sorry, Turing machine, NFA acceptance. So this language, it takes, this problem, it takes an NFA and it takes a string input, and we want to check whether or not this NFA will accept this string, hopefully you recall. And so like the same for if it was a DFA, you want to check if the DFA accepts some input string. I think if you remember from the tutorials and maybe from the lectures, we know from the lectures that DFA acceptance is decidable because they proved it, right? So if you don't remember, just take my word for it. DFA acceptance is decidable. But if we kind of like squint a little bit, if we want to solve NFA, basically just solving DFA acceptance, right? Because, well, okay, so they both have like a similar like structure of input. So they take like a finite automata and a string, and they want to see if that finite automata accepts that input string. Well, the NFA input, what if we just like, turn it into a corresponding DFA, right? Because, well, we taught you guys the subset construction method. So that's like a way where you can transform an NFA to a DFA. And now that you've got like the corresponding DFA and the string's input's still the same, well, why can't you just like, put it like, then just use that existing decider for DFA acceptance and like use that, and then you get your answer, right? Maybe I'll draw it. Okay, so maybe a cool diagram. Right, okay. So let's say this is okay, let's say whatever, that's good enough. Oh my gosh. Who designed this? Okay. So let's say this is a Turing machine for yeah, this is the wrong slide. Whatever. NFA acceptance. This is what we want to construct to show that, and this is what we want to construct to show that NFA acceptance is decidable. What does it take? It takes like this is an NFA and it takes an input string. So this angled brackets means it's like a string encoding. And then what does it output? It outputs like a decision, yes or no. Like, is it in the language or not? Is the string accepted by the NFA? What we're doing is we're just using like this is like the Turing machine for a DFA acceptance. Okay. And then we take this NFA and then we turn it into, let's say, B prime. We keep the string. So B prime is the corresponding DFA to the NFA B, and we get it from using the subset construction method. Okay. And then we put it into the decider for DFA acceptance, and it will say yes or no, right? So if it says yes, that means our original NFA, does accept the string. If it says no, then our NFA doesn't accept the string. Does that make sense? Okay. Hopefully it does. Okay. Right. And this, yep. Okay. Oh, yeah. All right. So that was a specific example, but you saw how we used DFA acceptance to show the decidability of that we knew that was decidable, and like the solution to that to solve NFA acceptance to show that NFA acceptance was decidable. So let's put it in more general terms, like let's have arbitrary languages A and B. So when A is reducible to B, so we show that when we say reducible, it means B can be if B can be solved, then A can be solved. So if B is decidable, then A is decidable. So we saw that because DFA acceptance was decidable, then we showed that NFA acceptance was decidable. Okay. Yeah.
And we also commonly use the notation of A brackets and B, or is that also a way to demonstrate reducibility where we use that notation?
Oh, yes, like the angled brackets.
Yeah. No. A less than or equal to M.
Oh, mapping reducibility.
Oh. Yeah. Oh, so maybe that's coming next. Sorry.
Oh, yeah. Good question. Oh, hi. Yeah, we'll look into that.
We're going well.
Yeah, it's going well.
Oh, okay. So that's so far so good. Now, okay, this next line here, we're actually not adding new information. This is just the contrapositive of the line above. Is everyone comfortable with that? Contraposition. So we have A is reducible to B. If we have like a A that we know is undecidable, that means we have a B we know that B is undecidable. So this direction I think is a bit more interesting actually than this direction above. But okay, so we'll talk about that later. First, we'll talk about mapping reducibility. So Harrison's question. Okay, so before when we were talking about reducibility, we're just saying like if A is reducible to B, that means you can use B to solve like a solution to B to solve A, right? So we didn't really put too much restriction on that. Now with mapping reducibility, we'll like put a bit more restriction. But first, okay, let me draw a bit. So with the example of NFA acceptance being reducible to DFA acceptance, we had this rough outline, right? Like we had this visualization where, man, we don't like technology in this subject. Where this is not like other computer science subjects. All right. So it kind of looked like that, right? We took like an input and then we sort of transformed it a little bit, and then we just put it into the DFA decider, DFA acceptance decider, and then we just took whatever like result we got from the DFA decider, whether it was yes or no. But in general reducibility, like we're not, you don't have to just do it like, we're not restricted to just like we take just the answer that we get from, let's say, DFA acceptance. We can do something like this where we take like an input, we do some like transformation, and then like we feed it into decider for like, let's say the language B. After that, we can like maybe do something, I guess we'll call it like post-processing. So a common example is like maybe, okay, I'll just do like ticks and crosses. So maybe this decider for B, it said like, okay, yes, it's in, accept the string. Maybe we can invert it and say no, and then vice versa. Okay, so in general reducibility, you can do that. You can even, like, you don't even just have to call this once. You can like call this like multiple times, like this subroutine, I guess we can call it. Okay, this is getting a bit messy. But, okay, what I'm saying is we can't do that for mapping reducibility. Okay. So, okay, let's first maybe, okay, I guess when I was writing this slide here, it looks like this is just a jumble of information. So now I'm putting some pictures. This part where you get the string and you do some transformation, there's some restriction to that. So that is actually done by this mapping reduce function, sorry, mapping function, we'll call it F. Okay, so it takes like, you know, like any string, and then it turns it to any other string. In terms of like generally. Okay, so we say F has to be computable. That means, well, that basically means it will always hold. So it will take the input, it will turn it into the output, and it will hold. So maybe like the output is, it's left on the string, on the tape. Okay. So, okay, well, do you remember in our example for when we were turning the decider, sorry, like the machine, the NFA, we're turning into that DFA, right? Like, how do we argue that it would always hold? It's because we gave you the subset construction method, right? And we know from class that that will always hold. That is computable. So, like in similar questions, you should give like reasoning generally, like to argue that your transformation is computable. It will hold like that. Okay. So we have this notation that Harrison mentioned. So it's like the less than or equal to sign, but with a subscript M. We'll talk about that later, maybe, like why it looks like that. So A is mapping reducible to B. So a bit more formally, right? So if we have like a string W that's in A, that means we've applied the F mapping to it, and then fed it to B. And let's see, is it in B? If it is in B, then actually in the first place it was in A. But if it wasn't in B, then it wasn't in A. All right. And yeah, I said we couldn't do any inversion or anything. And you can see, okay, so from the example earlier, NFA acceptance is mapping reducible to DFA acceptance. And we just like sort of described with like normal sort of natural language English like why that was sort of the case. But now we see that it was actually a mapping reduction specifically, not just a general reduction. And so that means we can give like this function f. So what did it do? It took, because the input for NFA acceptance is the NFA and the input string, so it takes that, and then it turns it so it keeps the string W, but it turns the NFA into a DFA with the subset construction method, as we mentioned. So yep. Is there any questions about that? Okay, I have a question for you then. Why do we have this symbol like the less than or equal to with the subscript m to denote reducibility? Why does it look like the less than or equal to symbol, like in general arithmetic? Yeah, yeah.
I can give a wrong guess.
Say it makes more sense for it to be the other way. To say that we're reducing.
Oh wait,
Oh, that
the number of like problems like hardness, like how it's solved.
yeah, you're on the right track.
But I know it's not a very formal definition. But it's like to the scope of problems it could solve, right? Something to it then.
Yeah, maybe I'll flesh that out. But I also like your point. It's a bit unintuitive. Like if A is reducible to mapping reducible to B, why does it make it look like that A is kind of like smaller to B? So yeah, maybe that's a bit confusing. But we will spell it out. All right. So if you remember, okay, how do you go to? Oh, you can use a scroll wheel. That's cool. All right. So remember this, right? A is reducible to B means if B is decidable, that means A is decidable. If A is undecidable, that means B is undecidable. So with mapping reduction, oh yeah, I forgot to mention. It was why do we have this distinction? Oh man, why do we have this distinction of mapping reduction and general reduction? It seems kind of arbitrary, right? Well, okay. So sorry. Before I answer this question, let me go on another tangent. So yeah, why like what's the point of making this distinction? Well, we can use mapping reduction to reason about recognizability, not just decidability. But we can't do that for general reduction. So let's see. So let's say like this, we look at this messy image on the right, and let's say now we're going to talk in terms of recognizability. Well, okay, now these boxes, they're not deciders anymore. Now they're recognizers, meaning they can loop forever if they don't accept the string, right? Okay, so let's say it goes through the usual process. It does this transformation, and then it gives this transformed input into like the inner recognizer. Okay, and let's say afterwards, what we want to do is invert the answers. Okay, well, let's say the string is not in the transformed string is not in the language of this inner recognizer. Well, what happens if you have a string that's not accepted by a recognizer? It can halt, right? But there's another problem. Maybe it doesn't halt. So if it doesn't halt, well, what we wanted to do was invert it, right? But if it doesn't halt, then we can never get to the inversion stage. And because we wanted to invert it, we wanted the outside recognizer to say yes, accept the string. And for a recognizer to like, if a recognizer has to halt if it does accept the string, right? But there's a problem. Like it may not halt. The inner one may not halt, so we might never be able to do that inversion. Does that make sense? Okay, so why did I make the tangent? Because, okay, so mapping reducibility, we can also reason about recognizability. So hopefully I've convinced you of that. So here, when we're talking about if we're talking about mapping reducibility, we can just like, substitute these words, decidable, undecidable for recognizable, unrecognizable. Okay, so let's have arbitrary language. A is mapping reducible to B. Oh my gosh. All right. So that means if it was if B is decidable, that means A is decidable, right? But we also have an additional thing. If B is recognizable, then A is recognizable, right? That sort of follows from what we've discussed. So we're not just talking about one like thing, decidability. Now we're talking about decidability and recognizability. And in fact, I'll tell you, I think you can also talk about this in terms of like P, like polynomial time, maybe NP complete and stuff like that. Don't worry about it, it's not examinable. But let's just say if B is easy, we'll just use this word easy, then A is easy. So if B can be decided or recognized, then A can be decided or recognized. Okay. And then we take the contraposition. So if A, instead of easy, let's say it's hard, so it's not decidable, it's not recognizable, then B is hard. Oh. Okay, I won't finish that word, but you know what I mean. Okay, so well, what does this look like? It basically means that like A, it can never be harder than B if you look at these two sort of statements. And conversely, B, it can never be easier than A. So B is like the upper bound of difficulty of A, and A is like the lower bound of difficulty to B. Yeah, so that was a lot of like, maybe that was a bit confusing, but does that make sense? Does that, like what Harrison said earlier, does that sort of make sense as like the fleshed out version of maybe what he was trying to say? I'll take that as a yes.
We have less than or equal to the image. So if you have A less than or equal to B, then you have that the image of A under F is a subset of B. So the image of a set being, you replace every element of the set with the result of the function applied to each of the elements. So if you apply the reduction to every element setting, like all those in the set, that set is a subset of the thing reducing it. So that's why it's less than 3.
Yeah, sure. Thanks. I agree. Okay. Oh, sorry. Yeah, good idea. Thanks. Oh, all right. Cool. All right. I think for reducibility, the best thing to do is like examples to like help you understand. So, okay, we have this language or this problem where we take context-free grammar and we want to see, does it accept epsilon, the empty string? Well, okay, yeah, so this problem is decidable, but can you show it? Maybe I'll give you 1 to 2 minutes and maybe talk to your neighbors and then report back to me. Yep, go ahead.
To go for the first time that I missed.
Oh yeah, that's pretty good. I didn't do that first time.
Yeah. Did it go well?
Yeah, it's good.
Are there any questions or anything to clarify?
It's all good. There are questions on Zoom if you guys want to address them. Could you give an example of what a valid argument for the transformation would be?
Chat.
Sorry?
We can't read the question.
Oh yeah, my bad.
Cool.
Can you give an example of what a valid argument for I assume an argument for the correctness of a reduction is what it means, what the question is supposed to be.
Yeah, that makes sense.
I mean, if you something simple from the tutorial would be good enough. Like, yeah, I don't know. You come up with a function. You
Well, I guess if you want to show it's a mapping reduction, you have to prove two things. You have to prove that one, that it's reduction, which means that if you've got some member of a thing, let's call them A and B, on the left, right? You want to show that if the reduction, call the reduction F, then you want to show that F of anything in A is so if let's call something in A X. So you want to say that F of X is in B if and only if X is in A.
Yeah, like
Yeah.
Yeah.
So you just have to prove two things. Just something's in A, but only if something's in B.
This part.
So which is the same as saying that that the image of A under F is a subset of B. And then you have to show that the F is computable. And that we just do by, we don't usually go into much detail, we just sort of try to give an algorithm and wave our hands and say clearly it's correct, because we're not going to have much to do with the subject of this topic.
Yeah, maybe I'll tell them that like during like a break, answer those questions.
What was the second one? Just solve recognition.
I forgot to mention that we don't
solve recognition. I don't know how it solves recognition.
Oh, because I think what they mean is like when I gave like the visual graphic of like the inside recognizer, it may like never hold, right? But we don't care if it never holds, because if it never holds, it was meant to never hold. Like the whole thing.
I'm just having trouble parsing out what the actual proposition is here. Why general reducibility cannot? Yeah. I don't quite follow the question.
Okay.
I am. Yeah. So I need a that's what
All right. Let's all gather back. So does someone have any ideas for this question? How they'll go about it? Yeah.
And you can just put the decider.
Yep, you can build a decider. And that would show that this language is decidable, right? Because by definition. How would you do that if you have any ideas?
If it's not being judged, which it is, then you can try to basically like use the algorithm that you cross out the terminals and symbols, and you see the start symbol, and then go to epsilon.
Oh, I like that idea. So you're kind of using that example from the lecture about CFG acceptance, right? You're basically using that general sort of method.
No, epsilon when it stands for input, we're not talking about it's not a terminal, right? A terminal is actually symbol of the output. The empty string it's a string that doesn't have any symbols.
Oh yeah, true.
No, so when we yes, it's a symbol in the abstract sense, but it's not a symbol of a grammar. It's just something that stands for the image. So it's not part of the alphabet. It's not part of the terminal alphabet or the variant alphabet.
Maybe anyone else have any ideas before I go through the, or you're writing it on the board? Thanks.
I can look at this if you want.
Oh no, just do whatever you think is good. So maybe I'll ask for one more propositional. Yep.
My idea, I don't know if this is correct at all, but was to use the emptiness problem of DFAs, which we know is decidable, to construct an equivalent PDA to show that it's also decidable.
The emptiness
Turing machine that decides that uses that. The emptiness problem of DFAs.
So how would you use the emptiness decider to make a decider for this?
I didn't get to that, but that was my idea.
Well, intuitively, so if we're gonna, for this language, if we're gonna accept CFG, it won't actually be an empty CFG, right? It takes because it should accept epsilon, the empty string. Do you see the distinction?
Yeah.
Yeah. Cool. But I like the thought. Okay. What did I have for the answer? All right. So I reduced it to CFG acceptance. So if we recall CFG acceptance, it so given a CFG and an input string, that's what I did, right? Yeah. Then does it accept it? So I think this is kind of like the gist of the answer that the first respondent basically said. So we just denote this language that from the question as EA. Why did I name it EA? CFG. It's mapping reducible to acceptance of CFGs. All right. So no, the EA CFG just denotes this whole language part. I just forgot to name this. It's like just let EA CFG equals that. Yep. So I'm basically saying we can create a decider for this language with the decider for CFG acceptance. How do we do that? Well, this mapping function, it takes the input, which is the CFG for EA CFG. What it does, it doesn't do anything to it actually. All it does, it puts an extra epsilon, and that should be like the input string. So now there's an encoding with the grammar that hasn't changed, and like a candidate input string, and it feeds it into the decider for Turing machine acceptance. So if the decider for Turing machine acceptance says yes, that is, then G accepts epsilon. That means G is a context-free grammar with epsilon is in its language that it generates. And if it isn't, then then it isn't, right? Does that kind of make sense? So do you see how we built the decider for EA CFG with and so you remember in the lectures that CFG acceptance was decidable. So because the acceptance problem for CFGs is decidable and we have a decider, therefore the EA CFG from this question is decidable. So if you remember, now this is so this was this direction, right? So we show that EA CFG was reducible, mapping reducible, but generally reducible to CFG acceptance. So and CFG acceptance was decidable. That means EA CFG is decidable. Does that make sense? Sounds like a jumble of letters. All right. Cool. And well, how would you argue that this mapping function is computable? Well, all it does is just append this epsilon to it, right? So that's kind of obvious. Maybe it's, yeah, okay, cool. All right. No questions? Or yes questions? All right. So we've used this direction. So if A is reducible to B, and if B is decidable, then A is decidable. So now let's focus on the cooler direction. If A is undecidable, then B is undecidable. So I guess we have this general, so we're using this, yeah. So we have a general format or template to use this statement. And what it is basically like a proof by contradiction. So similar to the pumping language. So you first you assume that B is decidable, and then we construct like a decider using that decider for B. We construct a decider for A. So I guess we can talk about A is like, let's say it's like a target language, but that we have a specific target language A that we know is undecidable. For example, Turing machine acceptance, if you remember from the lectures, it was proved that that was undecidable. And so, and generally, like, that's like the common sort of target language. Okay, so supposing we have B is a decider, then we make the decider for, let's say, Turing machine acceptance. But wait a minute, Turing machine acceptance is undecidable, right? So how can it have a decider? That's right, it is undecidable, so it doesn't have a decider. This is a contradiction. That means B cannot possibly have a decider. Because, yeah, if we had B being a decider, we can necessarily show that A was decidable by constructing that decider for it. But, I mean, we can't because A is undecidable. So do you see how we have this template, like how it sort of maps onto this statement? All right, cool. All right. So this was an example from the lectures. They use reducibility to show that the problem of Turing machine emptiness was undecidable. So Turing machine emptiness, it takes Turing machine, let's call it M, and it just checks if the language it produces is empty. So it rejects everything. So the point of this slide was kind of more like I was gonna talk about like how our general like format sort of maps onto like this example. So I'm not sure if you guys want me to go through like this example specifically, but I'll first go through like sort of the steps that happen. So our target language is Turing machine acceptance. So we prove that Turing machine acceptance is reducible to the Turing machine emptiness, right? But Turing machine acceptance, wait a minute, that's undecidable. So we have this relationship. Turing machine acceptance undecidable, then the Turing machine emptiness is undecidable. Okay, so how does like the proof by construction go? So supposing that Turing machine emptiness is decidable, that means we have a decider for it. Let's call it R. Using R, we will construct a decider for Turing machine acceptance S. Okay, so yeah, in the lecture they go through like the detail of what like the actual S is. First, I'll just say like, so we construct this S. So that means we've shown that Turing machine acceptance is decidable. But wait a minute, it's not actually decidable, right? So that's the contradiction. Actually, Turing machine emptiness is undecidable. So that's like the general template. Does that make sense how they use it in the lectures? So I have this slide and it's basically just what was said in the lectures. Do you guys want me to go through it, or do you guys don't worry about it, like I'll just continue? Hands up if you want me to go through it. Nice, I can skip it then. All right. Because yeah, probably nowhere because time constraints, and it was already said in the lectures. All right, so let's do this practice problem. So this time we have this language. Man, I should like name the languages for convenience. But so it takes a regular expression and it takes context-free grammar. So we want to see if they produce the same language, generate the same language. All right, so we say that this problem is undecidable. You guys, it's your job to prove it's undecidable. Okay, go ahead. I'll give you 1 to 2 minutes again. Talk to your neighbors and stuff. This one. Oh no, there's no this. Wait, yeah,
So the images objects that map select what the given just say form Turing Machines, so that you said computation, then you worked
I almost
like
this
you
is the
said,
last
operations. Yeah, no, that's all right. But basically, it's the same. Works so it's got the A object here. This is just a basic set. This
no
is
problem.
like
We'll
abstract
go how
concept,
far we can
but
go.
it's also applied to this and it so yeah, like for example, we can contain objects in numbers to and so you know we contain that in A and just say that's data, right? But we can also contain anything else. We can say Turing machine, Turing machine, etc. These can contain Turing machines, and we get, say, for example, you know the things like A, B, and
They built on the CPU.
Maybe that's.
I don't know what tools you have actually. I've just realized that I've been delivering the last lecture, so I don't know what tools you've been given to do this problem.
In the tutorials we had the universality for CFGs. It was mentioned that it was.
Yeah, you can see. Yeah, you can. Yeah, that
so I was
was
just saying, so Turing machine, these are just
Yeah,
to and so on and so on. Or like we can say there exists some this item here with an element of this set here. That's sort of what we're doing now, where the
well, if you are asked a question about reductions, you should be aware of all the things you know are decidable on the board. Well, basically,
it's weird.
it may be you may have in a situation where a question is really hard unless you know that I can reduce this to this very sort of straightforward reduction. But on the other hand, if you're weaker in other parts of the course, maybe focus on that instead, because this is just like what a week and a half of content. We can't ask that many questions about it, right? Sorry? Equality for context programming is decided. Equality for all things inside of the course. You check if they're the same thing, right? Equivalence. Yeah, so citing if two different context-free grammars, well, potentially the same, but they have the same language. That's yeah. You could also solve this using.
Yeah, wait 30 seconds more.
Wait, also. When I'm going to pay you before again, I was like,
Make me remember.
I think what it was.
Engineering with like methods.
Which engineer? Well,
And
which that's a really specific.
Maybe in the
Because this
one of the ones. No, like maybe last year or something.
last year.
Or last year or last year. One of them. Oh.
Wait, so I presented that and you were and now you're doing this. Wait.
Yeah,
Oh, okay. I was gonna say, wait, how are you tutoring this subject? But I was teaching you the same.
Should I funny?
Yeah, no, that's weird. That's funny. I hope it was useful. What a weird reverse. Yeah, so finally so we can fail it now. So the way scaling works is it's based on a percentage of what you again is or above. So it's not the number of people. So it depends on so the reason why we give these workshops is we give everyone false information. So everyone thinks badly and then it scales constantly. So
for lectures.
Yeah. So that's why we have it, and we haven't released the slides, so we can confuse you and make sure so that you're not first that exists. No, Mark is.
All right, come back. So, any ideas for this question?
Yeah.
Oh yeah. Hello, can I ask a question, please? Yeah, I think for now just type it, and then we'll have a break soon, and then you can like I'll have some time to answer more questions in depth. Sorry, I've not been attending to the chat. All right, so any ideas how to solve this? Any like rough ideas of things that might work? So following what I said earlier about how we had like a target undecidable language to show like to construct a decider for, what target undecidable language do you think would be a good candidate for this question? Any ideas?
Be something to do with the fact that there can exist a context-free grammar that's not a regular expression.
Oh, interesting idea. Is anything else you want to talk about that?
I was like thinking that we could get to a contradiction because both languages and grammars should be accepted, but then it was something to do with I don't know like whether, and this may be very wrong, but there's like certain ones can go on forever, so they will never also loop. Like I wasn't sure it's something to do with that as well with the properties of CFGs, but
well, before we get like your other point of maybe checking like if like let's say the context-free grammar is not regular. What if it is regular, but like what if both of those things make regular languages, but they're not equal anyway?
oh yeah, that's way simpler. Yeah.
No, that wasn't an answer.
Wait, so that
I'm saying like how would you check like if they're both
if they're both
like regular, but they're still like we still want to see if they're
one accepts on a no
Sorry, no. Sorry.
just show that I'm kind of like taking a guess in the dark. So does anyone you guys know, but I guess I was thinking at least something to do with just one word accepts and one word.
Well, sorry, I will
accepts
be
on a
there, but
different
like watching over
does not
you,
accept
make sure
the
that
same
you'll be good people.
string.
Oh, okay. Interesting idea. But there's like infinite amount of string, right?
Yeah, I mean not like an example, just like the abstract string like the I don't know. I'm just guessing. I believe it. I'm not.
No worries. Thanks for your attempt. That's a good some good thoughts. Sorry, did you have your hand up earlier?
It's again, it's like the empty set and proof the set
Whoa, okay. Interesting. Empty set. So maybe you're thinking oh,
assuming that also train to it.
so CFG emptiness are you preparing to?
No, I
But are you thinking of like using that as like the decider? Well, I think this is undecidable. Maybe. Good idea though. Good. Yeah.
There's a suggestion online. Could we use the fact that a set of all languages
this is decided strings, then we can just say that this is decidable. Then the universality one is
I like that answer. In fact, it's correct. Do you want to explain it or?
So we know that for a CFG is undecidable. And the universality is just saying that the language of the CFG will generate all strings. And so if we
Oh no, it was in the tutorial. They said it was undecidable.
Which tutorial?
Last week 12 tutorial.
and so I'm saying,
Yeah.
so what we need to prove to make this undecidable is saying that if you have a decidable this, then we can prove that the universality of the CFG is decidable, but it's not. So there's a contradiction. And so this is actually is undecidable. But we need a mapping from every CFG in the web and the universality CFG question to having what's R and G. And where I'm stuck at is how to everything as regulars.
Oh, okay. Thanks. Yeah, all right. So that's the correct answer. Maybe I'll talk about the concern. All right. So, okay, we'll just name this language EQRG. And yes, so all CFG is the CFG universality problem. So if you recall from the tutorials, so all CFG is, it's asking, given like a CFG, does it generate like all strings like sigma star, a Kleene star, Kleene star? Okay, and we're saying, so if you recall from the tutorials, we said that was undecidable, so you can use that as like a target undecidable language. So all CFG universality is mapping reducible to this language. So what is the mapping? So it takes, so CFG universality, it takes like the grammar, right? Just like grammar. And then the transformation is you're appending this R to it, and the grammar you're keeping the same. So R is a regular expression for sigma Kleene star. So I guess the concern was how do we make the yeah, Mac, thanks for your time.
15 minutes if there's people around, but I need to go for a short time.
Okay. So maybe, so how do we make this regular expression for Kleene star? So we see what we'll just, whoops. We'll just maybe from this grammar, we'll check out what this the alphabet is, sigma. And let's say like for example, e.g. it's like A, B or something. How would we make like a regular expression for it for sigma star? What if we just do like A union B Kleene star? Does that answer your question? Yeah, because I think in my opinion, I mean, it's pretty trivial and it's pretty clear that it's computable. And I guess Mac did mention, just then, like in these questions, we won't put too much emphasis on like proving the computability of like the mapping function. But like, so maybe if you give some like brief statement why you think it's like computable, maybe that's good enough generally. Okay, unless in the question it says like it emphasizes, okay, you should show like it's computable. Okay, so that's like some small details, but basically, so now we have uh the like a grammar and the regular expression that produces the language sigma star. So if we put that into this language, what it will do, or the decider for this language, what it will do is it will check whether this language of sigma star, that produced by sigma star, the regular expression for sigma star, and the language produced by the grammar, if they're equal. But wait, if we have that, then it just basically it answers the question of CFG universality, right? Because we're just saying if this G, like the CFG is equivalent to like another like G that's like it recognizes all of the strings. Do you sort of see how to? Yep.
We only do the like S equals on input general disability.
Yeah, so okay, the question was when we're gonna answer a question using general reducibility, I guess in the lectures they showed like sort of formats that had like S on input, like whatever the input is, and then blah blah blah. So that's a way where you can show you're constructing like a decided S. So and then the question is if we're showing if we're going to use mapping reducibility instead, can we just like maybe give the mapping reduction, like the mapping function? Yeah, I would say basically that is sufficient. So I would say give the mapping function and explain what all of like the like symbols you used mean. And maybe to like be sure if the question is like maybe a bit more marks, maybe it's like 3 or 4, 5 marks, maybe give some explanation. So just maybe like dot points you say. So if like if so for example in this one, if when Rn so the output of F is like this RNG. So if it's like if it shows that the grammar G is equivalent to the language of that grammar G is equivalent to the language of like sigma star, then that means you've shown that it should be accepted for CFG universality. And if it's not, it shouldn't be accepted for CFG universality. I think that would be a good amount of detail. And then, yes, I think you should get that mark for that question. Does that satisfy your question? No. So you can just take that as a black box. So for like this equality thing, well, for this equality checking thing, like we're supposing that like a decider for it exists, and we're going to run it, right? But like we don't have actually care what's like the inside guts, like the Turing machine description of it. Yeah, but I think if you're referring to, if you're, oh damn, the battery is running. Okay, let me go back to the previous slide. If you're referring to, let's say like the NFA example, you should say because we're using the subset construction method, so that's computable. I think that would be reasonable, and that's your justification why it's compute. Yeah. Does that satisfy your question? Okay. All right. So any questions about that? So we've shown that because this language, if it were to be decidable, then we can necessarily construct a decider for CFG universality, but we know it's undecidable, so contradiction. This language is undecidable. Great. Does that make sense? Any questions? Okay. That was... Thanks. That was it for the content. So some study tips and stuff. All right. Spam those practice questions and like the practice exams. There's plenty. And when you're in the actual exam, maybe don't spend too long on a question. Maybe, so if you remember like a common motif when we were reasoning about recognizability is like, if you have a recognizer, it might live forever, right? So don't let that be you. Don't be in a question where like, I don't know, you're like spending like too long on it. Maybe it's like unrecognizable or something. And then you get blocked and then you can't do the rest of the questions, which might be like decidable or something. So maybe do some context switching like we did, like we saw like some examples from the tutorial dimension and stuff. All right. Maybe let's have a break for 10 minutes. Or if you have any questions, then comment aside, should be happy to answer. Oh yeah. Then there's some exercise questions, but yeah, I don't know. 2 minutes.
I mean, if we do get time to actually do them, you guys can stay around with them. Otherwise, the slides will be posted somewhere. We'll let you know where sometime. I'll probably do a post on Andrew because I don't want to bother lecturers anymore. But like the recording will be out. There will be a video on YouTube as well because we're live streaming right now. Yeah. So it'll be somewhere. I'll let you know where. But yeah, you can access it later if you don't get time to actually do the questions. Yeah. But yeah, you can stay in the room until 1 o'clock because at 1 we have another workshop happening, of course, for models of design. So if you're doing that subject, you're welcome to stay for it. You're welcome to stay if you're not doing the subject as well. Yeah. So, right.
Thanks, Rama. Yeah.
Yeah, again, there are other questions now.
Which questions? The practice questions?
Yeah.
Sure. This question. You guys don't want to break? Yeah, okay, sure. I mean, yeah. While they are breaking down, they can have to while they're having a break. Okay. Yeah. Yeah, I'll set it on the Slack like a put it into later mass PDF together. Oh yes, I'll PDF.
There's stuff in the chat.
Idempotent.
Ooh.
These aren't the questions. Oh, okay.
Question about practice exam, question 8.
Bro. Man, maybe well, if you set up the questions for, but there's in-person questions as well. Maybe I'll go through the in-person questions first. You guys set up the practice questions, and then
Is it just the one that you sent me, Slack?
yes.
The question about my approach for question 2.
What was question 2?
The rate expression.
Oh, yeah.
So I that into the token. And then I had a conversation with
The latest one.
This one?
Nah, the latest. This one.
That one, okay.
If you share it again.
Yes, I can.
What you're doing? So this is our language that we're asking.
Okay.
Your
It's open on the web, and I'll just reshare the screen,
yeah. So that
and then you can access it.
this language like
Is that good?
like this language. The top language is
If we hide this one, I can
so
make it
that's
bigger.
actually the sure, direction.
Thank you guys for coming.
If you want to show
Thank you.
It's actually looks to
okay.
so what you want to do is using
For those of you who are online, we may need to close the meeting soon, but please know that the slides and any questions, everything like that, we will share them somewhere. Keep an eye on our stories on the CISSA page, and we'll share them somewhere. I'll try to do a post on it if I can, and I'll have everything,
We should be
all the
mapping
links
this
and all the recordings on this. But yeah, I may need to close the meeting in about 5 minutes. If you have last minute questions, please send them in the chat. Please post on it. Yes, I'll try. But yeah, if you have any final questions for our presenters, please put them in the chat. We apologize for not being able to get to the questions that were posted earlier. Some of them were pretty challenging. We couldn't understand what was actually written on there. But yeah,
we have
last minute questions we can answer them.
so you know CFG.
Thank you.
Yes, that's just every possible.
So that's our target. So we know.
Okay, so I think I understand. So we cannot use the CFG since we cannot map.
I'm not saying that you can't use it, but the sample solutions we have like a target. Universality. I'm not sure if there's a way to CFG maybe, but this is the way of people might not want to slides.
Okay.